Section 1110, Taylor and Maclaurin series examples. So where we left off was with the derivation of the Taylor and the Maclaurin series. Maclaurin is a specific example of the Taylor series. So just very quickly, a Taylor series says this: if a function has a power series representation at x equals a, then we can find those coefficients by looking at the derivatives of f of x, evaluating them at a, and over n factorial. That came out of our derivation. I won't go through all of that, but that came out of our derivation. So our Taylor series would look just like this. It would be the series of the nth derivative of a over n factorial, those are our coefficients, times x minus a to the nth. And here it is in expanded form. Now, if a itself is 0, if we are centered rather than at a, if we think about a being 0, which we often do, a lot of times we want what is called the Maclaurin series, where we are specific to being centered at 0, then this power series expansion just becomes the nth derivative evaluated at 0 over n factorial times x to the nth, since it's x minus 0 to the nth. Okay, that's where we left off. We went through those repeated derivatives of just a generic power series, found out that that's how we can find those coefficients. So let's do it. So let's get in here and let's look at a couple of examples. So what if we were asked this question? We want to find the Maclaurin series and the associated radius and interval of convergence for the function e of x, okay? The exponential function. So if we want that, what we have to do is we need to find our c sub n's for the power series. So we need to find our c sub n's. We're going to assume for the functions that we're looking at that they do have a power series representation. We're not going to spend time on the proofs for those power series. Those can often be difficult, showing that the remainder of the Taylor polynomials go to 0. So we're going to get right in, just make an assumption that it does have a power series representation, so that f of x e to the x is actually equal to a power series, c sub n, times, now in this case, it says Maclaurin series. So we do have to be aware of the language here, that when it says Maclaurin series, that is very specific to the fact that we are centered at x equals 0, or you could think of a being 0. So we are centered at x equals 0, which means that this is actually just c sub n times x to the n. Change that back to black. Since we are centered at 0. So when we read Maclaurin series, we think, okay, my a is 0, that means I'm centered at 0. This will be c sub n x minus 0 to the n, or just x to the n. So this is the case where we're looking for the nth derivative, the c sub n's, the coefficients, evaluated at 0 over n factorial. So that's the goal. We have to figure out these coefficients. So that's the process. That's what we're going to have to do. Once we've got those coefficients, once we actually have a power series representation, we'll get into the second part and look at that associated radius and interval of convergence. So how do we do this? Well, we've got to find a pattern. So let's think about it in tabular form. If I'm thinking of 0, 1, 2, 3, that should be good enough for this one, out to the nth index. And then let's think about what would be those nth derivatives of this function. And then once we have those, what would be the actual coefficient, which is the nth derivative evaluated at 0 over n factorial. And we're going to try to do enough of these so that we can see a pattern and get down to the nth derivative here. So as we're going, remember that this is just representing the function. So the 0 derivative is just the function. By the way, we defined that up above and kind of glossed over that pretty quickly with the Taylor and the Maclaurin series. But that is the convention. The 0th derivative is defined as the function. So this is just e to the x. The first derivative is e to the x. You know, the exponential function was a good one to do for our first example because the derivatives are all the same. E to the x, e to the x, e to the x. And even by the time we get to the nth by the time we get to the nth derivative, it's still just going to be e to the x. And when I actually evaluate that at 0, that's just going to be 1. So this is going to be 1 over 0 factorial, which, again, we also defined, one other note, that the 0th factorial is defined as 1. And I'll write this too. F of 0 of x is the 0th derivative is just f of x. So we get 1 over 0 factorial, which is actually just 1. And then when I get to 1, I get 1 again, because I'm plugging in 0 here, e to the 0. By the way, this was e to the 0 over 0 factorial. This is e to the 0 over 1 factorial. So I get 1 here too. And then I've got e to the 0 over 2 factorial, which is just 1 over 2 factorial, or 1/2. And then I get e to the 0 over 3 factorial, which is just 1 over 3 factorial, or 1 over 6. And this goes on until I get to the nth, the generic nth term, and that's going to be e to the 0 over n factorial, which is just 1 over n factorial. And we can see from here now that c sub n, those coefficients, are actually just equal to 1 over n factorial. And that was our goal, to come up with a way to express the nth term. So now that we have the nth term, we can plug that back into the power series expansion, and it turns out that the function f of x, which is equal to e to the x, is equal to the power series from n equals 0 to infinity of 1 over n factorial times x to the n. And if I expand that out, that just is 1 plus x squared over 2 factorial, and I could write this as 1 factorial, plus x to the 3rd over 3 factorial, plus x to the 4th over 4 factorial, and so on. Right? That is my exponential expansion. So now we want to figure out, well, where is that true, right? Because as soon as we take a function, going back to what we talked about in previous sections, as soon as we take a function and say it's equal to a power series, we have to know where is it equal to that power series? What is the radius of convergence? So the next thing that we need to do is we need to find the radius of convergence. And that's just going to be a ratio test for us. We've done that. We did that quite a bit in the last couple sections. We looked at radiuses of convergence, intervals of convergence, and so we're just going to continue that. In the previous sections, we were given the power series representation. This time, we had to come up with the power series representation. So once we've got it, though, limit as n goes to infinity, we're going to have x to the n plus 1 over n plus 1 factorial times n factorial over x to the n, which is the limit as n goes to infinity of simply the absolute value of x when we reduce there. And these 2 factorials, everything is going to reduce in those factorials except for the n plus 1. There'll be a single factor on the bottom factorial left, n plus 1. And as n goes to infinity, this of course becomes the absolute value of x times 0, which is simply 0. And 0 is less than 1 always. Ratio test here, criteria for the ratio test. 0 is less than 1 always, and so therefore this is always true. And so by the ratio test, the radius is actually infinity. So therefore, the power series, e to the x, is actually equal to the power series from n equals 0 to infinity of x to the n over n factorial with a radius of convergence of infinity. That means 4x from negative infinity to infinity. That's what the interval of convergence is going to be. I didn't ask for the interval of convergence here, but since the radius is infinity, we could go ahead and add that in. If it was a finite radius, of course, we'd have to test endpoints. But this is very cool because what we have right now is we basically have said that an exponential function can be expressed by a power series for all x's. So this will converge to, this power series will converge to the actual function e to the x for all x's. And we can show that graphically, and I wanted to just jump over to Desmos and show you guys graphically what's happening here. And so if we can go to, head over to Desmos. If we jump over to Desmos, and let's get this, I think we can get this all on one screen. I'm going to get that graph in there. Yeah. Okay, so what you can see right there, I have actually graphed. This is e to the x. So in black here, you can see e to the x. And if I just start to look at the Taylor polynomials, so I'm going to look at the finite series here, the Taylor polynomials. We'll look at just the first term. The first term is just the constant one. So obviously that's not a very good estimation. But then we add up the first two, and then we have a linear function, and you can see that in red. Now if I add up the first three terms in the power series, we have a quadratic. And you can see that's the blue graph. And then if we add up the first three terms, and you can start to see that these graphs, these Taylor polynomials, are slowly starting to come in and approach that e to the x. If we get to if we take four terms, we have this, this is actually a fourth power polynomial. You can't see that, there is further if we go out here. This keeps going. And if we take the first five terms, and so notice what's happening is here, you're starting to see the actual convergence of the power series to e to the x. And it is happening. I mean, I have this graph from, I don't know, you can see, I think on your screen, from about -15 to 15, the exponential. But you can start to see these actual power series, these Taylor polynomials, you can see them starting to approach this function e to the x. And I actually did it here. We could expand this out. So if we graph this in green and we can watch this happen in an animation, we can start to see those are the Taylor polynomials, each of the Taylor polynomials. And notice, here, let's pause it out here at 23 or something. Out here at 23, you actually can't even see the difference. You can't see the difference from 0 to 15. Over here, you can start to see the little tail. This green tail right here is starting to approach the exponential. The exponential is basically right on the x-axis. It's so small at that point. But you can actually see those Taylor polynomials approaching, that convergence of those Taylor polynomials to this function. And it will happen across the entire number line, across -infinity to infinity. So even there, even at just the ninth term, by adding in the ninth term, you can start to see, you can see it's just barely, it's almost converged in this point. And we're all the way up here at like 1,000 is what we're seeing here. So that's what we're showing right here, is that this infinite polynomial, this power series, converges exactly to e to the x as we go out towards infinity in the terms, as we add an infinite number of these terms. Okay, so now that we have this is going to become one of our useful power series, this e to the x. We have a couple of useful power series right now. We could go in here and we could put them in. So far we've got our useful power series that we've been working with, and we're just building up a little bank of useful power series, but we would want to add this e to the x. So we have 1 over 1 minus x, which is the power series x to the n from n equals 0 to infinity, which is 1 plus x squared plus x cubed, and that is true for a radius equal to 1. Okay? Now we can add in e to the x. Now we have another power series from n equals 0 to infinity, 1 over n factorial x to the n, which is going to be 1 plus x over 1 factorial plus x squared over 2 factorial plus x cubed over 3 factorial, and this has a radius of convergence of infinity. Now the reason that I'm listing these useful power series, and as we go on and continue to create these, because we can actually use these for use to derive other power series. We spent a lot of time in 11.9 working with this guy, This was 11.9. But now we've got another one that we can add into that bank and we can use it. So with this example, I'm going to go ahead and do that. But I want to do one more because these were centered at, these are useful power series. These are centered, by the way, at, these are Maclaurin series. These are useful power series. I should have added in Maclaurin. These are both centered at x equals 0. So these are useful power series and they are centered at 0, which is a lot of times what we want to be centered at. But let's go ahead and look at, let's take this e to the x and let's expand this. Let's add a couple of parts here. So let's do, now that we have that, let's do, let's call that actually part A. Call that guy part A, and let's do part B. So part B, what if instead of looking at it centered at 0, what if I wanted the Taylor series? So let's find what would change the Taylor series for f of x. What if I shifted the center? So let's find the Taylor series for, yeah, f of x equals e to the x centered at x equals 5. Okay, so let's shift the center. So we're shift the center. So what if we wanted to shift the center? What would be different here? Well, we're going to be still looking for a function, before I go into my table, we're still looking to describe f of x equal to e to the x. We're still looking to describe that as a power series from n equals 0 to infinity of c sub n. This time, though, is going to be x minus 5 to the nth, and my c sub n's are going to be the nth derivative of that function, e to the x, but we're not going to evaluate at 0, we're going to be evaluating them at 5 over n factorial. Okay, so we got to figure out what is the nth derivative of e to the x evaluated at 5, and that's going to be over n factorial. Now, we could go ahead and, I'm going to go ahead and do a quick little table, but we've already kind of talked about the fact that that derivative of e to the x just remains the same. So there's not really, I mean, the pattern, I guess, to look at in that derivative is that it remains the same. So as we go and we expand that out, zero, 1, 2, 3, out to the nth derivative here, and we look at what is that nth derivative at x going to be, and then what is the corresponding coefficient, which is going to be the nth derivative evaluated at 5 over n factorial. As we go and we do that, of course, this is just e to the x, e to the x, e to the x, e to the x, dot, 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 e to the x. Okay? This is our easiest function to work with in terms of repeated derivatives because it remains the same. So, but that said, that would end up being, then when we look at this, this becomes e to the 5th over 0 factorial, which is just e to the 5th over 1. This becomes e to the 5th over 1 factorial, which is e to the 5th over 1. This becomes e to the 5th over 2 factorial, which is e to the 5th over 2. E to the 5th over 3 factorial, which is e to the 5th over 6. And of course, by the time we get out to the nth derivative, we would have e to the 5th over n factorial. Okay? And that, we'll put that in red, that is what our c sub n is going to be. So c sub n, and we might have noticed that without the table, I just wanted to show you, because again, this derivative is the easiest derivative to work with because it is the same. It stays the same throughout. That is not true of other functions. So I wanted to just show you how we can generate this table for any function and look for the patterns. So c sub n ends up just simply being e to the 5th over n factorial. So our function here, when we write our function out, I think I used f of x. Okay, so f of x equal to e to the x, centered at, I will make this little note, centered at x equals 5. Okay, so if we were to focus in on x equals 5 on the x-axis, the Taylor polynomial that would represent e to the x would be n equals 0 to infinity of e to the 5th over n factorial times x minus 5 to the nth. And expanded out, that would be e to the 5th plus e to the 5th over 1 factorial times x minus 5 plus e to the 5th over 2 factorial times x minus 5 squared plus e to the 5th over 3 factorial times x minus 5 cubed, and so on and so forth. Okay. Now, of course, we also want the associated radius of convergence. I should have asked for that when I wrote out the problem, but let's assume that that is always true. So we need the radius of convergence, and so to find that radius, we would take the limit as n goes to infinity of e to the 5th times x minus 5 to the n plus 1 over n plus 1 factorial times n factorial over e to the 5th x minus 5 to the nth. We're going to get reduction here. This is going to be the limit as n approaches infinity of all kinds of reduction. We're going to end up with just x minus 5 over n plus 1, because again, when we look at what the canceling of those factorials, there's going to be one factor, one extra factor in the n plus 1 factorial in the denominator, so n plus 1, and this is going to end up being the absolute value of x minus 5 times 0, which of course is 0, which is less than 1 always. And by the ratio test, therefore by the ratio test, the radius must be infinity. Okay, so this is true. This expansion here, this power series, is true for all x's for a radius equal to infinity. Okay, what if we wanted to do just two more quick functions with this e to the x to wrap out this example? So let's do part C. So what if on part C, what if I wanted to do this? What if I wanted to find the power series expansion of, and I'm going to do a couple here, of g of x, actually we'll make two parts, of g of x equals e to the negative x, centered at x equals 0. By the way, that could have easily been written as just find the Maclaurin series of g of x equals e to the negative x. Okay, just two ways to say the same thing. So find the power series expansion of g of x equals e to the negative x. What if I wanted exponential decay instead of exponential growth, right? E to the x is exponential growth, e to the negative x exponential decay. So I can go through the whole process again, look for the patterns in the repeated derivatives, come up with what it would be for my c sub n. But this is where I want to remind you that we have those useful power series, and we have now derived e to the x, right? And if I know what e to the x is, I can do the same thing that I did with 1 over 1 minus x. I can use that useful power series, and I can just make my substitutions here. And that's what I want to do. That's going to be simpler than going through the whole process again. So rather than going through the process again here, I'm going to use what we've already done. So let's use the Maclaurin series for e to the x, which is, and I'll just rewrite it here, it's 1 over n factorial times x to the n, or x to the n over n factorial from n equals 0 to infinity. Let's use that. So once we've derived a power series, we can utilize it to create other power series. So we've got e to the negative x, so g of x equal to e to the negative x would simply be the power series from n equals 0 to infinity of negative x to the n. It's 1 over, I should write that first, 1 over n factorial times negative x to the n, which simplified would be n equals 0 to infinity of negative 1 to the nth over n factorial times x to the nth. Now this again is going to be true when the radius of convergence, that's not going to change when I make that substitution here because the radius was infinity. If we had a finite radius, we would consider what happens when I replace x with negative x. Okay, that if we wanted to actually write that out a little bit, it's going to be a similar series to e to the x, but it's going to have that switch on it. And so we're going to end up with 1 minus 1 over 1 factorial times x plus 1 over 2 factorial times x squared minus 1 over 3 factorial times x cubed, and so on and so forth. Okay? So that is that power series expansion. Okay, let's do one more. What if I wanted to find let's do this guy. Actually, I think we're going to do two more. Well, we've got e to the x here. What if I wanted to find, actually, let's just do one more. What if I wanted to find the integral from 0 to 1 of e to the negative x squared dx accurate to 3 decimal places? Okay. Okay. We are finally at this place where we have an integral of a function, and this is super exciting. We finally have, and I don't mean that sarcastically at all, I actually mean that it really is exciting because this whole chapter has been building up to this sort of thing. We have a non-elementary, we don't know how to do this. This is a non-elementary integral. We haven't been able to do this, right? We've been like stuck here. We've been stuck here since our integration chapter, right? Where we talked about, we come across these integrals that we don't have integration techniques for. And now all of a sudden we are going to be able to actually integrate this. So how do we do that? Well, it turns out that e to the negative x squared has a power series expansion, which means that it can be represented by an infinite polynomial. And we can integrate infinite polynomials. Polynomials are easy to integrate. So if I can write e to the negative x squared as a polynomial, a power series, okay? So let's write e to the negative x squared as a power series. Then I can actually integrate it. So let's write that e to the negative x squared as a power series. E to the negative x squared, well, we just up above here, right, we're going to use the Maclaurin series for e to the x, which is 1 over n factorial x to the n. So we're going to do that, but we're going to replace x with negative x squared. So this would have to be equal to the power series from n equals 0 to infinity of negative x squared to the n over n factorial. We can simplify that a little bit because we're going to use that in an integral. So that's going to be negative 1 to the nth x to the 2n over n factorial. That, I'll just remind you, that is a polynomial. So if n equals 0, that is going to be, the first term is going to be 1, and then it's going to be minus x squared over 1 factorial plus x to the 4th over 2 factorial minus x to the 6th over 3 factorial, and so on and so forth. So we are now looking at e to the negative x squared. We're thinking of it, it's really just this power series. It's this infinite polynomial. But I can integrate those terms. I can easily integrate 1 and negative x squared over 1 and positive x to the 4th over 2. I can integrate those just by using my power rule. So now we can get in here and we can actually integrate. We can integrate the power series. Oh, real quick, I should say this. This is true when the radius of convergence, or where, I should say, where the radius of convergence is actually infinity. That means that x, this is for all x. This is true across that entire interval. So this isn't even just going to be specific to the interval 0 to 1. That's all we're looking at it here for. But this is true across the entire number line. And so we can actually come in here and we can say, all right, well, let's integrate it then. So the integral from 0 to 1 of e to the negative x squared. So now let's integrate. I should write that first. So now integrate with the power series, right? We couldn't integrate the function, but we can integrate the power series. So now integrate with the power series. So let's get in there, 0 to 1, e to the negative x squared dx, and we can integrate 0 to 1. That's equivalent, right? We can use this equality here. This is equal. That's equal to the integral from 0 to 1 of the power series, negative 1 to the n, x to the 2n over n factorial from n equals 0 to infinity. And integrating a power series, this goes back to what we've talked about before. We can integrate term by term. The radius will not change when I integrate, so I can actually, let's actually integrate. I forgot my dx. Let's integrate each term. So we're going to end up with, and I won't have an integration constant because this is a definite integral, so I'm not going to have an integration constant. So normally we would put the plus c out in the front, but we're not going to have an integration constant. We're going to be plugging in our values here, so we're going to get negative 1 to the n, x to the 2n plus 1 over 2n plus 1 times n factorial, evaluated from 0 to 1. Okay? And that's a power series that I can actually plug in. This is x equals 0 and x equals 1. So essentially we're looking at a power series evaluated when x is 1 and when x is 0, taking the difference, just using our rules here. So this is going to be the power series from n equals 0 to infinity of negative 1 to the nth times 1 to the 2n plus 1, but that's just going to be 1, over 2n plus 1 times n factorial minus n equals 0 to infinity of 0. Right? All right, so this integral from 0 to 1 of e to the negative x squared dx is actually equal to the power series from n equals 0 to infinity of negative 1 to the nth over, I'm going to center that a little better, negative 1 to the nth over 2n plus 1 times n factorial, which if I start to expand that out, right, we could actually look at that. If I expand that out, that's going to be 1 minus 1 over 3 times 1 factorial plus 1 over 5 times 2 factorial minus 1 over 7 times 3 factorial plus 1 over 9 times 4 factorial minus 1 over 11 times 5 factorial. I could keep going. I don't think I need to go this far, but 1 over 13 times 6 factorial. And this keeps going. The reason I wrote those out is because there was one other piece that we haven't talked about yet. It said estimate this accurate to 3 decimal places. So if we need to make this accurate to 3 decimal places, we have to actually use an estimation theorem. And so the estimation, this is an alternating series. So we're putting together all kinds of pieces here. We're going to use our alternating series estimation here. If we want this sum to be accurate to, this power series to be accurate to 3 decimal places, remember what the alternating series theorem says. It says that you can add up the terms until you get to a term that is less than what you need. So the b sub, by the time you get to the b sub k term that is less than your remainder here, then you can stop. So if we actually look at this and we expand this out, this was one of the easier estimation theorems to use because you could look at just the expansion. So if I actually, and I did this on the calculator to try to save a little bit of time, so I'm going to write these out. So this ends up being 1 over, so we got 1 minus 1 over 3 plus 1 over 10 minus 1 over 42 plus 1 over 216 minus 1 over 1360, and that's actually where I can stop. So remember, we wanted to be accurate to, over here, we wanted to be accurate to 3 decimal places, which means we wanted our remainder to be less than 1 over, 1,000. So we want our remainder to be less than 1 over 1,000. And so that occurs, this term right here, notice that this term is less than 1 over 1,000, which is what we wanted the remainder to be. We want the remainder to be less than 1 over 1,000. That term is less than that. So if I were to add up the first, and again, this is 0, so this, we call this the 0 term. So if I were to add up 1, 2, 3, 4, the first 5 terms here, this sum will be accurate to within 3 decimal places. So we can say that this integral, the integral from 0 to 1 of e to the negative x squared dx is approximately equal to, and when I add those up, again, I did that on the calculator as well, that becomes 0.747, and that is when the actual remainder of doing that, and that was the first, 1, 2, 3, 4, 5 terms. So the remainder of using 5 terms is actually less than 1 over 1360, which is, of course, less than 1 over 1,000. So that means that we are accurate to 3 decimal places. Just pulling together what we did back in the alternating series section. So kind of pulling that in here, if we wanted to actually integrate to some amount of accuracy, then we can add up the certain number of terms until we get to, if it's an alternating series, until we get to a term that is less than our hopeful remainder. Okay, all right, I know that was a long video, guys, but I wanted to get all of those exponential examples into one video and show you all the things that we can do once we have a power series expansion. All right,